Good day, statisticians. Today, we're going to talk about the fundamental principle that we use to make the prediction about some response variable based on an explanatory variable when we know there is an association between those variables. So imagine we have some type of positive association that exists. It's pretty obvious that if I can use, when I know about that association, to make a prediction about the response. The way that we make predictions that we're going to see here is called regression to the mean. And so today's video, we will hopefully understand how our predictions that we make that are based on a line are really predictions that regress to the mean, that always go back to the mean. So let's start with like a basic example. Suppose, right, imagine this. Imagine you, a statistician, are doing a very statistician-y thing to do, right? You select an adult male college student at random, and you try to figure out how tall that person will be. So how tall do you think a randomly selected adult male college student will be? I have no way of knowing either, right? Who knows, right? Well, if I don't know anything at all about a particular person and I'm going to guess how tall they are, I'm going to assume that they probably are fairly typical if I don't know anything else, right? And so this person's height, what would I guess? Well, if I didn't know anything, I'd probably guess that this is a normal, typical person. So I'd probably guess, I don't know, whatever the average is, right? So what's the average height? Well, I could do some research and try to figure out what the average height is for students in this particular college. And oh, look, there you go. So in this particular college, the average was about 69.53 inches for the adult male students. And we know there was some variation, a standard deviation of 2.12, but knowing nothing else, I don't know whether to go above or below average. I would just guess average, right? Okay, great. What if I knew something else about the student? Let's say I knew, right, that the student was above average in weight. Above average in weight. What would probably be true about the student's height? Well, would that student also be above average in height, or below average in height? Well, I mean, any of those could be true. We know that there is variation, right? We know there's always variation in students' heights, and we know it's possible that a student can be above average in weight and below average in height, or above average in weight and average in height. We know all three of these are a possibility, but which is most plausible? Well, in my head, if I think about what the association probably looks like, if I had, say, some type of, here, let's say a scatter plot where this was the height, and I was predicting heights based on weight, what do you think would be the direction of the association that exists here? I don't really know. If I had to guess, I'd direct that association is probably positive, right? And heck, we could collect some data and we could find out that in fact, in a sample, at least from this university, the correlation was 0.63. If that's the case, that is a moderate positive association. I don't know. We'll look at it. Maybe we'll look at a scatter plot, but if that's something like that, then I would guess, yeah, if a student is above average, right? So here's the average weight, this would be X bar, then I would guess that they would probably be above average in height as well. That would be probably my best guess. If some student is up here, they're probably above average in each. Does that guarantee it? No, right now. And so we could take a look at our scatter plot, and there we go. And here in this scatter plot, we see something that kind of looks like this guy I estimated right there. And it seems like most of these folks, average would probably be right around here. Most of these folks who are above average in weight are also kind of above average in height. So that's a pretty reasonable guess. And notice that all of our predictions, all of these things that we're saying, really were going back to the mean. We were regressing to the mean, right? We always go back to the mean. The mean is sort of our focal point in making any type of prediction. But I would like to make more specific predictions. What if I knew the exact value of a student's weight? Could I come up with an exact guess of a student's height? And I'll tell you right now, it is possible just by knowing how strong that association is, right? Knowing that the correlation is supposed to be, say, 0.63, right? Between these variables, knowing that and knowing certain facts about, say, the mean weight and the mean height, I can use these three facts, and also knowing their standard deviations, knowing the standard deviations of X, the standard deviations of Y, knowing these facts here are sufficient for me to be making some predictions. So what does regression to the mean look like when we're actually doing stuff? Well, there's two kind of key principles theoretically, right? When we're doing regression to the mean, the first fundamental principle is basically this. Without any further information, we expect an individual to be average. right? Just sort of like the student here I didn't know anything about. If I know nothing about you, I'm going to guess your average. Now, sometimes I'm willing to guess something other than average, right? So supposing there was a second variable and I knew that some type of association existed between my response, say height, and another variable. Well, I'd be willing to depart from my guess of average based on the other variable, so long as that association was pretty strong, right? So the stronger the correlation, the more your prediction can vary from average. All right, let's just try to see that in a couple of just completely contextless general scatter plots, right? So imagine we have these three scatter plots right here, as we can see. In each of these, we can imagine making the average y value our prediction, right? Our prediction. Let's suppose we know that an individual takes the explanatory value 8. Right? So in all three, let's say in all three cases, we know the value of the explanatory variable is approximately 8. In which of these three scatter plots is the mean of y, represented by a blue line, is the mean of y the most, a very plausible estimate for the value? I just lost the cap of my marker. I'm going to grab it. In which of these three is guessing for an individual who takes the explanatory value 8, is the mean of y, represented by the blue line, of the most reasonable guess, right? Well, that would be in the first one right here, I think, right? If we look at this guy, right, we could see the mean of y, right, is for 8 seems pretty close to where a lot of the dots are, right? It would be really, really bad for this last one here. If I look at the explanatory value 8, right, for x, I'm not going to guess the average of the y coordinates in this situation. I would guess something much higher, kind of up here, right? Why? Because the strength of this correlation is so strong that it seems silly to guess the mean of y in this instance. Here, guessing the mean of y doesn't seem all that implausible. This correlation is extraordinarily weak, right? Something in between here, I still probably wouldn't guess the mean, but it would seem like it wouldn't be as terrible of a guess. The place where it would be the worst possible guess would be this last guy right here. And so that we only can make our predictions for what a response variable is vary away from average if we see a really strong correlation, or the stronger the correlation, the more we can guess away from average. So let's just imagine putting those principles in play with thinking about the same example, guessing someone's height from their weight. So let's say Hank is some student at this college, and here we have the scatter plot of some results we got from taking a sample. And we say we know Hank is about average in weight. What would we guess to be Hank's height? All right, well, average in weight is 176.37 pounds based on what I see here. And so what do you think we should guess? Well, remember, our principle was, without any further information, we'd expect an individual to be average. And in fact, in this case, I know the student is average in weight. So what am I going to guess? Probably average in height. And so that is that sort of math. That is the first mathematical way that principle comes together. That if we know your average in one variable, we're going to predict your average in the other. In other words, if the point mean x, mean y, right, is always going to be on the line. The point mean x, mean y is always on the line that we use to make predictions, right? And so let's see that right here, right now. Was that true for here? Here's the line of best fit that would be generated by technology, right? Let's check here. This is apparently the line of best fit for that scatter plot. What I'm telling you is that the mean of x should be predicted to be the mean of y. The mean of x is predicted to be associated with the mean of y. So let's see here. If I plugged in the mean of x, so my equation was 59.599 plus 0.0563 times, all right, what was the mean of x? It was 176.37. Here I got 69.528. Boom, right? That height of 69.53 inches is the exact thing that I'm predicting on this line itself. So the lines we come up with will always predict that the mean of y is paired with the mean of x. So that's kind of nice. It's regression to the mean. Everything comes back to the mean. All right, now suppose though we have an individual that varies from the mean, right? Say Kyle is 1 standard deviation below average in weight. Let's predict Kyle's height. All right, well, this is a little bit trickier, right? If I know Kyle is below average in weight, let's predict his height. Well, all right, so average was 176.37 pounds. We know he's 1 standard deviation below average. He's probably below average in height too. How many standard deviations below average in height do you think he is? Well, if he's 1 standard deviation below average in weight, he's maybe 1 standard deviation below average in height. Well, the correlation though isn't super strong, right? And remember that we should only make our guesses move away from average if there's like a strong correlation. The stronger the correlation, the more our prediction can vary from average. Well, let's just say here, let's say for instance, let's see what this line actually predicts, right? Let's say how much does Kyle weigh? Well, if Kyle was 1 standard deviation below average in weight, that would be 176.37 minus 1 standard deviation, that would be 23.73. That's 152.64. So Kyle, right, his weight is 152.64, right? So let's figure out what his predicted height is supposed to be based on the line. Right now, based on the line, I'm going to say that's 59.999 plus, missed a 9 there, plus 0.0563 times his actual weight, which was 152.64. So let's plug that in and see what we get. 59.999 plus 0.0563 times 152.64, and we get 68.59 inches, right? Just noticed I typed in something wrong when I was doing this. I was like, that answer isn't what I expected. I guess I gotta flip a marker. All right, here we go. First try, caught the marker. Oh yeah. Just noticed I typed in something wrong when I was doing this. I was like, that answer isn't what I expected. Notice that I typed in the equation wrong. It's not 59.999. It's 59.599, silly goose. So it's 59.599 plus 0.0563 times 152.64, right? So actually, okay, so we're predicting 68.19, not 68.59. And so how far off is that from average? 69.53. That is 1.337 inches below average, which is not quite a standard deviation. A standard deviation was 2.12 inches. So how many standard deviations is that? Let's divide that by 2.12 and there we go. Negative 0.6308 or so. Does that look familiar to us? How many standard deviations below average do we go? 0.63 standard deviations. Check it out right here. Do you see the correlation between these variables was 0.63? Is that a coincidence? It is not a coincidence. So actually, as it stands, when Kyle was 1 standard deviation, right? For Kyle, we see Kyle is 1 standard deviation below average in height, right? One standard deviation below in weight, right? We predict that he's in fact 0.63 standard deviations, right? Below in height, right? Why? Because the R value in this case was 0.63. And so the mathematical principle is this. When we're trying to make predictions that are for values that are different from average, we're going to use z-scores, right? If the individual is z standard deviations from x bar, then we'll predict the response to be R times Z standard deviations from the average of Y. Okay? So if I know, you were 1 standard deviation below average in one variable, then I'll predict that you were R times 1 standard deviation below average from the mean of Y. Pretty cool, right? If something is 2 standard deviations below average, right? Say that the correlation, right? The correlation is 0.63 still. If I know that a value is 2 standard deviations above average, I can do 0.63 times 2, and I'll guess that that individual is 1.26 standard deviations above average, right? 2 standard deviations above average in X, because of the correlation is only 0.63. I'll guess it's 1.26 standard deviations above average in Y. So let's look at that in a particular example here. A physics teacher collected data on a math placement exam at a school for each student in her class. Right? She then plotted this data against the quiz scores students had on the content from that week. The plot was linear. So, okay, we've got this situation. Here's a scatter plot, right? So let's say probably the math score is going to be an explanatory, and the quiz score for the physics will be a response. And so we plotted this, and we see some type of linear plot. Do you think this correlation is probably positive or negative? Probably positive. Right? It's math and physics, right? If you do better on a math test, you're probably going to do better on a quiz. So as it turned out, the correlation was 0.55, which is telling me that it's going to be some type of positive. Is it going to be strong, moderate, or weak? Well, definitely not strong, just barely moderate. Maybe something kind of like that. I don't even know. I'm just guessing here, right? R is 0.55. Okay, so there we've got this correlation. All right, so let's imagine, let's be told the quiz scores, right? These quiz scores have an average, a mean of 86. So let's say the mean was 86, right? Boom, 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 boom. And so, okay, that'd be kind of in the middle of the scenario if we think about that. And there's a standard deviation of 12, so there's a decent amount of variation away from the mean. So the idea here is, of course, regression to the mean. If I know a student if I don't know anything else about a student, I don't know anything about their math score, what would I guess to be their quiz score? Well, if I know nothing about your math score, I'm guessing that your physics quiz score is going to be an 86. However, if I know something about your math score, I might have my guess potentially vary away from 86. Now, if your math score is exactly right, average, then I would definitely guess that you are average in the quiz score. Now, if you're below average in your math score, then I might guess you're below average in the quiz score and stuff like that. So let's look at a particular student. A student's math placement exam score was 0.8 standard deviations below average, and he scored an 80 on the quiz. All right, so this student, right, was below average in their math score. So they're somewhere down this way, right? 0.8 standard deviations. I don't know how big a standard deviation is, but they're somewhere down this way. And I know their score was below average in Y. They got an 80. So I don't know where 80 would technically be. Let's say 80 is right here, right? And so this student might be like maybe right there or something like that. So the real question is, all right, did he do better or worse than predicted on the quiz? Well, how could we figure that out? How could we figure out what we should have predicted? All right, well, we know this student did 0.8 standard deviations below average on the math placement test. Therefore, did the student also do 0.8 standard deviations below average in the quiz? Well, no. Remember, our correlation is R, right? And so we would expect this student to do not exactly, but we know the z-score of x was 0.8. So we don't expect the z-score, the z-score of our predicted y to be also exactly 0.8. We expect the z-score of our predicted y to be R times the z-score of x, right? Our correlation X. And so we know that if this student was 0.8 standard deviations below average, negative 0.8 there, and we know the correlation is 0.55, then we would predict that the z-score of this particular student should be 0.55 times 0.8. That would be negative 0.44 standard deviations below average, right? And so this is what I would expect. So, okay, this is what I'd expect to be for the quiz score. So remember the quiz scores, right? The quiz scores have a mean of 86 and have a standard deviation of 12. And so I would expect this student to be 0.44 standard deviations. Remember, this is the unit here is standard deviations. 0.44 standard deviations below average in their quiz score. So I could say, okay, how many is 0.44 standard deviations? Well, I could do negative 0.44 times 12, the standard deviation. And I get, let's see here, 0.44 times 12 is 5.28, right? And so, okay, then that would mean I'd predict that this student will be whatever the mean of y is, right, minus 5.28. In other words, I'm going to predict that this student is 86 minus 5.28 points. So 86 minus 5.28, supposed to be an 8, and I get 80.72. So how did this particular student do on the quiz relative to expectation? Did they do better or worse than predicted? They actually did really gosh darn close to what we would predict. Fun fact, right? This student, right, they actually got an 80, right? So the residual, right, the residual for this particular student, the value minus the predicted y, is just 80 minus 80.72, which is negative 0.72. So they were really, really, really close to what we'd predict. They actually did a little bit worse than what we would predict. Oops, a little bit worse, 0.72 points lower than predicted, but gosh darn, it was pretty close, right? The fundamental principle here, though, is notice this, that we can make a prediction for a response variable based on an explanatory just by thinking about how many standard deviations a value is below average in X, and guessing that you're going to be a similar number of standard deviations away from average in Y, but sort of scaled back, brought closer to the mean, right? Regressed to the mean, ultimately based on the correlation. The stronger the correlation, then the closer the more your prediction will be able to vary from the mean. However, the weaker the correlation, the closer and closer and closer that your prediction for Y is going to get to the mean. Guys, I hope this kind of helps. Hope you learned something. This is doing our best here, being sick. But sorry I can't be with you today. Have a very beautiful day and luck in your homework.